So, let f from M to n be an A module homomorphism then 1 kernel f is a submodule of M, image f is a submodule of n, and third one, image of f is isomorphic to M modulo kernel of f. So, I think the 1 and 2 are easy verification. A proof for the third one you have seen for groups, probably for rings as well, but let us quickly recall. So, suppose you have define a map phi from M mod kernel f to image f by phi of x bar equal to f of x. So, in this case we have to prove that it is well defined, because there could be many representatives for x bar. So, if x bar is equal to y bar, what does that say?
X minus y belongs to.
Yeah. So, these two equivalence classes are same, implies that x minus y belongs to kernel f, which implies that f of x minus y is 0. Since f is a module homomorphism, this says that f x equal to f y, which implies that phi of x bar equal to phi of y bar. This implies phi is well defined. Okay. Now, why is phi a homomorphism? Because f is a homomorphism. So, phi of x bar plus y bar is f of x plus y. So, this is x bar plus y bar by definition of addition in quotient module. This is same as x plus y bar. So, let me write phi of x plus y bar, which is equal to f of x plus y, which is same as f x plus f y, which is same as phi x bar plus phi y bar. So, for all x bar y bar in M modulo kernel f, and for A in A and x bar in M modulo kernel f, phi of A times x bar, again by definition of scalar multiplication on M mod kernel f, this is same as A multiplied with x bar is same as A x whole bar. By definition of phi, this is f. Since f is an A module homomorphism, this is equal to A times f of x, which is A times phi of x bar. So, therefore, phi is an A module homomorphism. Okay. Why is this injective? So, okay, first let us see why is this surjective. Can you immediately see that it is surjective? every element of image f is of the form f of x for some x in M. So, therefore, take its image in M mod kernel f x bar, phi of x bar will be f of x. So, let y be an image f, this implies there exists x in M such that f of x is equal to y, and that implies phi of x bar is equal to y, that implies phi is surjective why is phi injective? If phi of x bar is 0, what does that mean? Sorry? Yeah, that is true. So, one can directly go back from here. This implies this, or this implies f of x equal to 0, which implies x is in kernel f, which implies x bar is 0. So, therefore, this phi is injective, this implies phi is an isomorphism, and that proves the third statement. Okay. So, this is the proof is pretty similar to the proof that you have done for groups and for rings. There are some interesting consequences, as in the case of groups or as in the case of rings and so on. If I have suppose I have M1 contained in M2 contained in M. Okay. So, A modules, which means M1 is an A submodule of M2 and M2 is an A submodule of M, and hence M1 is an A submodule of M. Then M mod M1 mod M2 mod M1 is isomorphic to M mod M2. This you have seen in the case of groups as well as rings, right. If you have in the groups, what did you prove? If H if you have something like this, then G mod H modulo K mod H is isomorphic to G mod K. So, and R mod I, if you look at J contained in I contained in R, J and I ideals of R, then R mod J modulo I mod J is R mod I. So, this is an exactly similar statement. Now, how do you prove this? I mean, I said this is a corollary of first isomorphism theorem. Yeah. So, from M mod M1 define, let us say phi from M mod M1 to M mod M2 by phi of, so to talk about different representations, let us write x plus M1 this equal to x plus M2. First of all, this should be well defined. Is this well defined? If I have two different representatives for, let us say, x plus m1, that means x plus m1 is equal to y plus m1, which is same as saying x minus y belongs to m1, but m1 is contained in m2. Therefore, x minus y belongs to m2, and hence x plus m2 is same as y plus m2. So, this is well defined map, and one can check that this is a homomorphism. Okay. So, phi is well defined, and phi is an A module homomorphism. Okay. So, now what is the kernel of phi? Kernel of phi, by definition, it is set of all x bar in m mod m1 such that x plus m2 is 0, or in other words, I mean to say 0 plus m2, or in other words, this is a set of all. So, let me use this notation itself, x plus m1 in m mod m1 such that x minus 0, which is x is in m2. So, this is precisely, by definition, this is m2 mod m1. So, by first isomorphism theorem, m mod m1 modulo the kernel, which is m2 mod m1, this is isomorphic to m mod m2. Now, suppose you have
don't we need to show surjective to actually?
Oh yes, correct. So, this is phi is yeah, this is again another phi is surjective. Why is phi surjective? If you take any x plus m2 in m mod m2, then look at x plus m1, and phi of x plus m1 will be x plus m2. Therefore, it is surjective, but yes, this needs to be shown. Now, suppose I have two submodules m1 and m2, submodules of m, then we can, as in the case of groups and ideals and so on, one can define m1 plus m2 this, by definition, this is set of all x plus y, x belongs to m1, y belongs to m2. This is called sum of two modules, and this is again an A module. This is again an A submodule of M, and take, if this is I in I is a family of submodules of A submodules of M then you can generalize this definition of sum of two modules. Then one can define summation mi I in I, this to be set of all x I in I, but then whenever we deal with rings, modules, groups and all these objects, we do the addition operation only finitely many times. We do not talk about infinite addition. Okay. So, therefore, what we do is, what we say is that x I equal to 0 for all but finitely many I. Now, one can talk about another application of first isomorphism theorem. This is one application. Another application of first isomorphism theorem, again similar to what you have seen in groups as well as in rings, that if M1 and M2, okay, so maybe I will write this as a proposition. First, let me just write this as a statement. If M1 contained in M2 contained in M are A modules, then M2 mod M1 is an A submodule of M mod M1, and M mod M1 modulo M2 mod M1 is isomorphic to M mod M2. That is the first statement that we proved earlier. The second statement is, if M1 and M2 are A submodules of M, then what can you say about this GH mod H? This is, so, or HK mod K or IJ, sorry, I plus J mod I. Now, these are some things that you must have seen in your group theory, group and rings theory course, right. This is isomorphic to H mod H intersection K. This is isomorphic to J mod J intersection I. Similarly, you want to say this is isomorphic to M2 mod M1 intersection M2. So, how do you prove this? Again, think of as an application of first isomorphism theorem. Define a map from M2 to this one. So, define phi from M2 to M1 plus M2 mod M1 by phi of x equal to x plus M1, or we will just say, since there is no confusion, we will just say x bar. Here we do not have to worry about well definedness, because there is no question of two representatives and so on. This is a module, any element has its own existence, there is no representative issue here. So, this is a well defined map. We need to say that this is a homomorphism. Is that clear? It is a homomorphism. Again I will phi is an A module homomorphism. Phi of x plus y is x plus y whole bar, which is x bar plus y bar, therefore, which is phi of x plus phi of y, and A times the same thing. So, therefore, it is a module homomorphism. Now, if we prove one more, there are two more things. What is kernel phi? Kernel phi is all elements in M2, x in M2 such that x bar is 0, or in other words, all elements in M2 such that x belongs to M1, which is same as M2 intersection M1. So, now what remains to be proved? Do we have to talk about one? Yeah. So, what we need to show is that phi is surjective. How do you prove that it is surjective? How does any element here look like? M1 plus M2, any element in M1 plus M2 looks like some x plus y bar or x plus y plus M1 as a coset. Yeah, it is y belongs to, so if I take x in M2 and y in M1, y belongs to M1, which means x plus, so let x be in M2, y in M1, then x plus y whole bar, this is same as x plus y plus M1, but then this is same as, by definition in the quotients, this is same as x plus M1 plus y plus M1. But what is y plus M1? Which is same as 0 in quotient module. So, this is equal to x plus M1, or in other words, this is same as x bar. For that we need a representative, x is in M2. So, if I take any x in M2 and y in M1, this implies that phi of x is equal to x plus y bar. So, this implies that phi is surjective. So, therefore, by first isomorphism theorem, M1 plus M2 mod M1 is isomorphic to M2 mod M2 intersection M1. We have already shown that the kernel is M2 intersection M1. Now, when we talk about summation, then next that should probably come to your mind is product. But in the case of modules, there is no product, right. When we talked about ideals I and j, we talked about the product ideal ij. But if you talk about two submodules of M, say M1 and M2, we can't talk about M1 M2, right, because there is no product defined on modules. But then there is another product. We have a product. What kind of product? Scalar multiplication. So, one can talk about what is called, for any A in A and M in M, AM is well defined. So, what kind of product you can think of in this case? If I take any set S and subset of A and M an A module, then one can talk about SM, right. But what would how would you define this to be? Yeah, again as in the case of ideals we saw, we are not only talking about AX where A is in I and X is in J. We have to talk about their summation, then only you will have a structure on that, otherwise it will be just a set, it will not have a structure. We are interested in studying structured sets. So, here if I define this to be equal to summation, if I define to be AX where A belongs to S and X belongs to M, there is no problem, but that will not make any sense, it will just be a set. So, instead what we do is we take AI xi finite summation with AI from X and okay. So, most often we in this case a small observation that if I look at, let I be the ideal generated by S, what does that mean? I take all finite linear combinations of elements of S with elements from scalars from R, the ring A. Okay. So, if I is the ideal generated by S, can you relate I M and S M? There is immediately there is an inclusion, which is this is contained here. Can we say this is contained here? Yeah. If I take any element here, how does any element here look like? Summation AI xi where AI belong to I and xi belong to M. Now, how does any AI look like? Any AI look like summation, let us say alpha ij sj, some finite summation. Here also I should say Sij, because for each I there could be different sets, different elements. So, therefore, this summation AI xi looks like summation alpha ij Sij xi. Now, alpha ij xi is again in M. So, therefore, you can think of this as Sij times some element in M. So, this belongs to Sm. Okay. So, this Sm and Im are same, therefore, we will stick to, most often we will stick to Im, but then there are some simple cases where we use the notation Sm. For example, if your set S is singleton A, then we write AM instead of ideal generated by, they are the same. So, this is set of all AX, X belongs to M. So, this is one such place where we use this notation SM. Okay. Now, well, this we defined this set, and we saw that if I take I m and S m, they are the same if I is generated by S. Is this an A submodule? 0 belongs to it. And for any x here, minus x is here, x is of the form some summation a I x I, or just take minus of a I for each, right. So, additive inverse is there, additive identity is there, the its addition is abelian is kind of, it comes from the module itself and so on. So, therefore, this one can see that this is, and scalar multiplication again it is straightforward verification. I m is an A submodule of M. Again, going back to the theory that we developed in the case of ideals, another object that we studied was if I take two ideals I and j, then looking at their colon, right, I colon j. So, in this case, if I have n and p be submodules of M, what can you say about, or how would you like to define n colon p? How would you like to define this? Does this make sense in the case of modules? Of course, we do not have a multiplication in modules, but then we have a hint lying here, right. What is the possible way of defining?
If x belongs to A, so that x be containing M.
So, I have this A m, we have just defined. If I look at an element A in A with, see, A p would be a submodule of M, but then we want to look at all elements which will multiply it and take it inside. See, how did we define I colon j? This was set of all x in A such that x j is contained in I, right. So, here see any ideal is an A module. So, this if I consider I as an module, an A module, this should be true, right. So, this what I want is this should be inside N, it is a submodule of N. But now what we have obtained is a set in A, not in M. So, the colon operation in modules give a set in A. So, if you have a set in A, what question would you like to ask? Where the first thing is, see, you are inside a ring. So, whether it has any of the ring structures. Is it just simply a set, or whether it is an abelian group, whether it is subring, whether it is ideal, there are lots of questions. So, what do you think about this set? If, for example, think of the situation where your M is A itself, okay, your module is A itself, and you take two ideals I and j, then they are submodules, and in that case the definition is same, right. In that case this turned out to be an ideal. So, in this case what would you expect? Would you expect it to be an ideal in A? So, first let us see whether this is, does this have 0? 0 is there, right. So, 0 belongs to n colon p. If x and y are in n colon p, what can you say about x plus y? X comma y in n colon p, does that imply x plus y is in n colon p? xp is inside n, yp is inside n is a submodule, therefore xp plus yp is in n. So, here one should note that x plus y, x plus y p, see our aim is to see whether this is contained in n. What we know is that xp is contained in n and yp is contained in n. So, if I take xp is in n, yp is in n, this is a submodule, this is a submodule. So, sum of both are submodules of n. So, their sum is also a submodule of n. This implies xp plus yp is in n. But is this same as x plus y p? There are a few things that you should is xp plus yp contained in x plus y p? Is convince yourself. Okay, but we are not really bothered about that. See, what is that we need to prove? We need to prove that x plus y belongs to, if x and y are in n colon p, whether x plus y belongs to n colon p. If x and y are belongs to p, so I take any x plus y p, so let p be in p, then what can you say about x plus y times p? This is equal to xp plus yp, xp is in n, yp is in n, therefore this is in n. So, this implies that, yeah,
since x plus yp is a subset of x plus yp, so it will be
this is contained here, this is contained here, yeah, that is true. So, we have the other inequality is true. So, therefore, this is p is contained in n. So, this implies x plus y is in n colon p. So, therefore, n colon p is closed under addition. Therefore, this is an abelian group. What about whether it is, if I take an element A in A and R in n x in n colon p, is it true that A x is in n colon p? X p is contained in n. Therefore, A x p is contained in A n, which is contained in n, right. X p is contained in n, this will imply that A x p is contained in A n, which is contained in n. Therefore, A x is contained in n colon p. So, what have we proved? N colon p is an ideal. So, this is an ideal that plays a lot of role in the structure of modules in various roles. For example, if you take, if M is an A module, then 0 colon M. So, take n to be 0 and p to be M. This is called the annihilator of M. Okay. This is called the annihilator of M. Now, if I take I to be, so denoted by if I is the annihilator of M, then see, in general A mod I is an A module, but so A mod I is also a ring, but you can't I mean in general you can't give a module structure to A over A mod I. Over quotient ring you can't give a module structure to the ambient. Similarly, if I have, if M is an A module, then M mod n is an A module. But if I take I to be an ideal and A to be a ring and M is an A module, in general we might not be able to say M is an A mod I module. Okay. Can we say, okay, so let me put it this way, let J be an ideal of A and M be an A module. When can we say give a natural module structure, A mod J module structure to M? Okay. Think about this question, we will take it up next time.